Felipe, Schuch from Porto Alegre in Brazil, and we're not going to look at a new flow configuration, but we are going to look at what we call a rapid prototyping tool inside Xcompact3d. So Felipe, please, you have 15 minutes.
Thanks, Silva, for the introduction. My name is Felipe. I'm glad to be here today representing our lab. LACET is the CFD lab here at PUC Rio Grande do Sul, and this is our work, Sandbox Flow Configuration, a rapid prototype tool inside Xcompact3d. Starting with the motivation for this work, there are two main points to highlight. The first is, how can we speed up our workflow? And I mean the iterations here in the scientific process, but more specifically, how can we speed up the iterations here in the simulation cycle, where we need to code, compile, debug, run many times. And the second point is, can we improve the learning curve for beginners in our code? And especially, how to help them to code new flow configurations, going beyond the benchmark cases. This leads us to identify the main challenges in our workflow. And if you would like to make it easier for beginners and faster for developers, I would say that the parallel decomposition is great for performance and scalability, but it takes a while to master allocation, transposition, and all the MPI calls. And besides that, coding, compiling, testing, debugging, and handling I/O infrastructure is not so easy. It's another point that we would like to improve. So the problem were identified. Now let's see how to solve them. This is the Sandbox flow configuration. Of course, Xcompact3d already reads the parameters file at initialization, but with the new module Sandbox, the entire initial setup can be imported from the disk. And using it, we can customize any new flow configuration with no need to recompile the main code. The initial setup case includes case-specific definitions like initial condition, boundary conditions, geometry, and others. And it can be provided externally. And our intention was to keep it simple, but using the disk is still very useful, because with it, the choice of what to use as this external tool is totally up to the user. It can be Fortran, MATLAB, R, Julia, Python, and many others, as long as you can write binary arrays in the same fashion that Xcompact3d will do. And here we have a good point. This framework can speed up our workflow, and at the same time, there is no extra dependencies to install. And besides, the core of the code was untouched. So we have the usual performance in the code combined with the flexibility for the initial definition. So in this way, we use the right tool for the right task. Here we see what we can do with Sandbox now. We should always specify the initial condition for velocity and scalar fields, but the other arrays are just demanded in specific situations. Like we can specify the inflow profiles for velocity and scalar if you use Dirichlet boundary condition where x is equal to 0. We can also set scalar values at the bottom and top boundaries if we are using Dirichlet conditions for scalar in y. We can set a customized operator if we want to impose a constant flow rate if the flow is periodic in the stringwise coordinate. And we can set the epsilon array if we are using immersive boundary method. Here is an example of how to set the initial condition in Python using numpy. We initialize the arrays with the right shape and data type. And then we can take advantage of Python's flexibility and readability to set the values for our flow configuration. Besides, we can combine it with other tools to plot, compute, and test our setup. And finally, we write them to the disk, so they will be available for module Sandbox. Here we see an estimation of the cases covered by Sandbox at this moment. we can simulate the channel flow, the flow around the cylinder, periodic hill, and TGV. The dense current in lock exchange will work too, as long as we are not using the low Mach number approach. It was not implemented in the module yet. Well, it's a work in progress. And the turbulent boundary layer demands more specific definitions for boundary condition and flow rate control, so it's also not supported yet. But like I told you, it's just an estimation, because now we can play around, modify the cases, and if combine the cases, like we will see. For example, we are going to merge the periodic channel and the flow around the cylinder, besides combine it with heat transfer in what I call the periodic heat exchanger. We have periodic boundary conditions here in the stringwise direction, and it's periodic in the spanwise direction as well. Cylinder is located at the center of the domain, and its dimensionless temperature is fixed at 0. We have no slip boundary condition at the bottom and top walls, and their temperature is fixed in 1. And now we'll see how to code it. I'm using here Xcompact3d toolbox just because I'm more familiar with it. We start here importing the package. And let's say that we already had set all the correct parameters in the input file. So now we can load it in our Python application. We start the dataset with the Sandbox function. And it returns to us the dataset with the right coordinates. Dimensions, coordinates, and the 7 data variables that we are going to work with now. We start setting the temperature as 1 at the bottom and top walls, like we specified in our flow configuration. Now let's set the initial condition for the stringwise velocity as this vertical profile, and in addition to some randomize, and just randomize for UI and use it. And the initial condition for temperature will be 1 everywhere. Now it's time to set the geometry, cylinder in the center of the domain. Note that Xcompact3d toolbox includes many methods to draw many standard geometry. Here we are using the cylinder. So we have to specify its center in X and Y. And we are good to go. Since the domain is periodic in X, we need to specify a forcing term to maintain a constant flow rate. And as you can see here, Xcompact3d will compute the flow rate with this integration. So we can customize this operator for the volumetric integration. And this one here will compute vertical integration and will give us a unitary value per high unit, besides including an average in X and Z. We multiply both top and bottom planes by half because of the composed trapezoidal rule for integration. And of course, we remove the geometry from our integration operator. And now it's time to write all the values to the disk, and we are ready to run the simulation. Note that there's no need to recompile the code every time. And we can code, test, plot, and debug the initial setup using any computational tool, like a Jupyter Notebook, and make it very interactive. Here we see an animation of the case that we just coded. Where is the animation? Sorry, the animation not here. You can access it's a toy model with low Reynolds number, but you are invited to access the complete code in this link here. And you can play around with the parameters, definition, and you can access the slides using the QR code at the end of this talk. And anyway, I have a few more examples to show to you. We are looking here in the top view again. Let me change it quickly.
We just saw it very briefly.
No problem. Yeah. So this one's a top view of the gravity current in axisymmetric flow configuration. It's just like Ricardo explained it to us early in his talk, but this time the denser fluid is starting here at the bottom left corner, and it can spread in more directions. And we can see the lobes and cliffs near the front, and some rings are formed in the body and they break down, and there are other nice features. And this is the last example, is the flow around a square with passive scalar as a visualization tool. Here at the inlet, we have this smooth step function for the passive scalar. And as a result, we can see this nice pattern downstream due to the turbulence. And as always, everything is very customizable. We could change the position of the square. We could include more square, change the number of steps here at the inlet. Everything outside the main code. And I have a special bonus for you. I've talked about improve the learning curve for beginners in our code, and here is another initiative. We have this user interface with IPy widgets under development in our lab. Using it, we can enforce the right relationship between the parameters, just to make sure they are what Xcompact3d expects. You can see here that we ensure that both boundaries in one direction will be periodic or not at the same time, and the number of mesh points change back and forth to be always a valid value. Very nice. So to conclude this talk, we expect to help users from different levels with our framework. For students in CFD, it provides a direct hands-on experience and a safe place for practicing and learning. And for advanced users and code developers, it works as a rapid prototype tool. Furthermore, it's a useful advance in terms of research reproducibility, because now it's easier to create, collaborate, and share any new flow configuration. That's it. Thank you very much for your attention. I'm ready to take any questions.
Thank you, Felipe. May I ask you, there are a few links in your presentation, if you can put them on the chat, because of course we can't click on your slide. I put the read the doc link of your Sandbox, but there were a few links in your presentation.
I don't know where's the chat right now, but I will send it soon.
Yeah, you will have to stop sharing to see the chat eventually. Is there any question? So most of the stuff that Felipe is doing, we're going to discuss them next week. We have a small developer meeting for the advanced developer of the code. So this is something we are going to be discussing next week. I had a question, Felipe, but I forgot what it was. It was at the start of your presentation. I will ask it to you when I remember. I completely forgot what it was. So no questions for Felipe? Very good. Anyway, if you have some question, please feel free to ask on the chat. And Felipe will also be giving a presentation next week as well at the developer meeting.
Okay,
right.
Thank you.
Thank you very much. Thank you, Felipe, for your the link and for the slides.